Okay. We are now in the next section, which is 17.3, which deals with glycerides. And before we get moving on, we should cover what glycerol is. We talked about it in the alcohols chapter. It was one of the common alcohols you had to memorize in that chapter. But in case you've forgotten, glycerol is 1,2,3 propane triol. And if we draw propane, so this is a molecule of propane. And if we put an alcohol or an OH or a hydroxyl on every one of those carbons, so if we put one here, if we put one here, and if we put one here, this is a glycerol molecule. There we go. So glycerol. So glycerides must have something to do with glycerol, and they do. And it says here that glycerides are lipid esters, so they're lipids, and they're also esters. And I mentioned that really early on in the lecture in this chapter. I said we're going to see esters in waxes, and we'll also see them in glycerides like triglycerides. And it says here that an alcohol group from glycerol will form an ester with a fatty acid. So essentially what we're going to do is we're going to take a fatty acid, so, you know, some kind of long chain fatty acid like this, and then we're going to combine it with an alcohol. So I'll just put ROH, and then we're going to produce an ester, right? But the alcohol is in fact coming from glycerol. So the alcohol will be one of the hydroxyls of glycerol. Anyhow, and what else is important is that esterification reaction, right? When we take, so esterification, right? Let's write it down here. Acid plus alcohol to give us an ester. That's what esterification is. It was the bonus question on your last, or one of the parts of the bonus question on your last exam. The esterification can occur at 1, 2, or all 3 of those hydroxyl positions. So it doesn't have to happen at all of them. It could be at 1, it could be at 2 of them, or it could be at all 3 of them. If it happens at 1, we get what's called a monoglyceride. If it happens at 2, we get a diglyceride, and 3 gives us a triglyceride. And triglycerides are really important. It says here that a neutral triglycerol or triglyceride, a triglyceride, we can also call it a triacylglycerol or a triglyceride, right? Sometimes we call it a TGC. Triglycerides are non-ionic and non-polar, and we will look at the structures that help us rationalize as to why TGCs are non-polar. And it says here that TGCs or triglycerides serve as energy storage in fat cells, or what are known as adipose cells. Again, glycerides are lipid esters, so let's look closely at the formation of a monoglyceride. And we start off with our glycerol molecule. This is the exact same thing that I had drawn on the previous slide. If I draw the bond line structure of this molecule, right, I have 1, 2, 3 carbons. I have a hydroxyl on the first, second, and the third. So I have my 1, 2, 3 carbons. I could number them here, 1, 2, and 3. It doesn't matter. If we combine with 1 fatty acid, we make a monoglyceride. And of course, we still have 2 hydroxyl groups that are free here. And we also produce water in the reaction. Now you might be wondering, where's the acid? You know, where's the H plus? Has that been left out? Did you make a mistake? No, the acid and heat, that is not required because we're talking about biological processes here. And so the formation of a triglyceride or a monoglyceride in this case occurs in a living system. And so the reagent here would actually be, let me erase all that, would be some kind of enzyme. And an enzyme is nothing more than a biological catalyst. So some kind of enzyme, and if you're wondering, well, what enzyme is it? Well, that depends on the monoglyceride that's formed. But I just want you to understand that we're not going to do reactions in the human body with sulfuric acid, right? We generally frown on that kind of thing. Anyhow, a TGC or a triglyceride places fatty acid chains at each alcohol group. So you can see here that stoichiometry is very important. So if we have 1 mole of glycerol, for example, we have a 3 in front of the fatty acid. So that means that we would need 3 moles of fatty acids, right? Because we're adding one here, here, and here. All right, so that covers the stoichiometry a little bit. And then we get a triglyceride. Let me just show you one quick thing in case anybody in our class is a real YouTube or internet hound and loves to look up everything on the internet, which I don't have any problem with that whatsoever. But sometimes glycerol is drawn like this. So sometimes people will draw it like this, which is just a real, kind of shorthand form like that. And I use this form sometimes too, right? So this is our CH2 or our methylene at the top. This is the methine, right? So it's not uncommon to just see people draw this on the internet or even in an organic chemistry textbook. It's a perfectly legitimate way to draw glycerol to make a really quick and pretty triglyceride. I'll show you an example later on. Let's talk about the difference between fats and oils. And I alluded to this a little bit earlier on, but I think it's really fun to look at these I guess these are space filling models down here of two triglycerides. You have tristerin and triolene. And before we get into that, it says here that fats are the combination of glycerol and fatty acids. Fats mainly come from animals and less fish, and they're solid at room temperature. And I told you that's like your bacon grease that solidifies, or your beef fat or something like that that solidifies at room temperature, whereas oils come mainly from plants and fish and are liquid at room temperature. And this picture, a picture is worth 1,000 words, right? So it's not totally easy to see it here, but the point is that you see these atoms that are red, those are oxygens, right? So this is where the glycerol is. So this is our glycerol backbone right here. But what's the difference between these two molecules? Tristerin is made of glycerol and 3 molecules of stearic acid, which is a saturated fatty acid. And you see how the tails are really straight. They're all perfectly straight. Whereas in triolene, it is made from linoleic acid and glycerol. And you can see that there's a kink in each one of these, right? It kind of looks like, the first one looks like a shuttlecock from badminton, and the second one looks like a broken shuttlecock from badminton. But the whole idea is that tristerin can pack much more effectively, and what's the result? It has a much higher melting point of 72 degrees. So tristerin is a solid at room temperature, right? You have to warm it up to 72 degrees to get it to melt, whereas triolene is a liquid at room temperature, right? Even if it was a really cold outside, it would still be a liquid down to -4 degrees Celsius. Kind of interesting stuff there. Triglycerides have the typical ester and alkene chemical properties, as they are composed of the two groups, the fatty acids and the glycerides. And what's beautiful about triglycerides, which are naturally occurring molecules that can be isolated from plants or animals, is that human beings can take them and we can use any kind of synthetic reaction that has been developed in the lab, like esterification or hydrogenation or saponification, and we can affect those reactions upon a triglyceride. So let's walk through them quickly here. It says here esterification. If we take a fatty acid, we're just talking about fatty acids right now. If we take any fatty acid and we react it with the hydroxyl of an alcohol, and we could choose whatever alcohol we want, we can form an ester, right? That's what esterification means. It means, let's just write it here, formation of an ester. You can't come out of Chemistry 102 if you don't know what esterification means. The next one is an old chestnut that we haven't looked at in a while, is hydrogenation. Okay, you think about, we looked at hydrogenation of alkenes and alkynes to reduce them to alkanes, and we also looked at the hydrogenation of ketones to produce secondary alcohols and aldehydes to produce primary alcohols. But now we're going to go back to the alkene thing, and we're going to talk about the hydrogenation of double bonds, and that's going to help us understand where trans fats come from. Okay. Next, it says glyceride reactions. We can take a glyceride or a triglyceride and we can hydrolyze it to regenerate the fatty acid in glycerol. And then we can also hydrolyze a triglyceride with base, which is saponification. And we've discussed saponification at length, right? We use a strong base like hydroxide. And again, this is how the pioneers and people on YouTube still make soap. In fact, if you go on YouTube and look up saponification or, primitive soap making processes, there's all manner of people out there that are doing this, for giggles, I guess. Anyhow, this is a review, so I have some good news. If you're tired of listening to me after 73 minutes, the good news is that esterification is a reaction that you've seen many times before. But before, when we talked about esterification, we just talked about carboxylic acids, maybe like acetic acid or propionic acid or butyric acid. But now we're talking about using what? A fatty acid. So a naturally occurring carboxylic acid with a long hydrocarbon tail. And we can do the exact same reaction that we could with a smaller carboxylic acid, and that we would treat the carboxylic acid with an alcohol in acid, and we'd heat it up to drive off what? To drive off H2O. And in the process, we form an ester. So there we go. We could make a fatty acid ester. Sometimes we call them that. The next thing is we're going to talk about addition to the double bond. Now, before I get into the chemistry, I just want to point out some, kind of idiosyncrasies of the book. Down here, they put the structure of linoleic acid. Now, they left out the fact that these are cis double bonds. They didn't draw it. I don't know why. They didn't use the bond line structure. Maybe it cost too much money in printer's ink or something. But anyhow, we've got two double bonds in linoleic acid, and we did look at the structure of it earlier on, and we can hydrogenate the double bonds in an unsaturated fatty acid the same way that we hydrogenated an alkene or an alkyne. Now, before we get into that, I just want to remind you that hydrogenation is an addition reaction. What are we adding? We're adding hydrogen. And you should remember that hydrogen is a diatomic molecule. Hydrogen, when it's in a pure sample, doesn't just exist as H like this. It exists as H2, right? It's always bound to another hydrogen atom. And there are other atoms that do that, like nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All right, so sometimes my students like to use the acronym Brinkelhoff to help them remember that. Some people like the acronym Have No Fear of Ice Cold Beer. Either way, you need to know all of the diatomic elements, of which hydrogen is one. And it says here in the second bullet point that unsaturated fatty acids can be converted into saturated fatty acids. And hydrogenation is used in the food industry all the time. In fact, I'm sure most of you have heard of things like partially hydrogenated vegetable oils. If you've ever spent any time reading a label of foodstuffs, you might have seen something like that before. So what's being shown here in this reaction is nothing more than taking this naturally occurring fatty acid, linoleic acid, and treating it to the conditions of hydrogenation. So using nickel, they could have used palladium or platinum as a catalyst, but they chose nickel in the book. And then they're using two molecules of H2. Why do you need two molecules of H2? Because you're adding one molecule, I'll write it below. You're adding one molecule of hydrogen here, and you're adding another molecule of hydrogen here, right? Because you need to convert this into a CH2, this into a CH2, and these as well. Okay, so that's a total of 1, 2, 3, 4. 2 times 2 gives you 4. Now, look at what happens here. It says here that unsaturated triglycerides can be hydrogenated, and this slide shows complete hydrogenation. So we take all three of those double bonds, and we convert all of them to single bonds. Notice that there's an error in this reaction in that they didn't balance out the equation. So let's do it. If we're going to put hydrogen, and let's choose a catalyst, we'll choose nickel. Again, how many molecules of hydrogen would I need to affect this hydrogenation reaction the way that it's drawn here? Who could tell me? Yeah, thanks, Tyler. You'd need 3, absolutely 3, because we have 1, 2, 3 double bonds that we're going to hydrogenate or reduce. Now it says here that we can control the hydrogenation conditions so that only some of the pi bonds will be reduced to give those partially hydrogenated fats. In fact, that is how margarine is made. Margarine is made from unsaturated fats, or basically vegetable oil, and then they subject it to hydrogen gas with using nickel as a catalyst, and they stir it, and they keep subjecting it to hydrogen, and they stir and they stir and they stir until they get to the desired consistency where it is spreadable. But even after you take it out of the fridge, it's still spreadable, unlike butter, which will, put a hole in your toast or something like that. Anyhow, so what happens is during the hydrogenation process, and this is beyond the scope of our class, the actual chemistry of how this occurs, but you'll just have to take my word for it, that it says here that some of the cis carbon-carbon double bonds can undergo an isomerization to produce trans double bonds. So trans fats are actually produced during the hydrogenation of unsaturated fats. And so what can happen is you can do that isomerization. Right here we have the two hydrogens on the same side of the double bond, and so that is cis, okay? And then here you can see that they're on opposite sides, and so we get a trans fat. And trans fats have been implicated in the raising of cholesterol levels, and of course the cascade of events that can follow from having high cholesterol levels. So kind of some interesting chemistry here. So now you can tell your friends that trans fats, in fact, are not natural. They are man-made, and they have, been shown to possibly cause deleterious effects to human beings' health. The next reaction we want to look at, some more good news, some review, is glyceride hydrolysis, and we're going to look at acid hydrolysis. So if we take an ester and we treat that with an acid, here's our acid, and heat and water, of course, because hydrolysis, right? We need water for hydrolysis. We can produce a fatty acid and an alcohol. Notice, something I just want to put this bug in your ear is if you're irritated by, some of the things in organic chemistry, if you think back to just a few slides ago, I said if you combine a fatty acid and an alcohol and you heat them up with acid, you end up producing an acid plus water. And now I'm telling you that if you take an ester and water, heat them in acid, with acid, you make a fatty. Like, well, how do I know which one it is? That would be a very good question, and I'm sure that if we were face-to-face, I guarantee somebody would ask that question. And I can answer that for you. Basically, it boils down to this molecule right here. It boils down to water. So if you were going to do a hydrolysis reaction, what you would do is you would stir the ester in a huge amount of water. So you'd have much more water than you would the ester, and so that will actually drive the equilibrium towards the hydrolysis to produce the fatty acid and the alcohol. The opposite, if you want to take a fatty acid, combine it with an alcohol, and do an esterification reaction, again, the key component is water. So what you have to do to get that reaction to work is you actually have to heat it up quite a bit hotter, and you can actually remove water from the reaction mixture. And if you're wondering, well, how do you do that? It's actually not that sophisticated, but it's kind of hard to explain. There are special types of glassware and apparatus that have been invented, that help aid in the removal of water. We can also use something that are called molecular sieves, which is basically just a big molecule that absorbs water. Anyhow, just to, if you have any questions about that, which would be totally justified, I just want to put that bug in your ear. Let's talk about saponification some more. If I can find my slide here, glyceride saponification. It says here that the saponification reaction is the base catalyzed hydrolysis of an ester, right? If we take a good old, ester, and we treat that with a hydroxide base like this, we will end up producing a carboxylate. I went over this in detail before with you guys, and you would also produce an alcohol. And of course, if we want to highlight that, this part, the hydroxyl, will actually be the part that's here attached to the alcohol, like that. Now, the products are an alcohol. So here's our alcohol right there, and an ionized carboxylic acid salt. And I told you another way to name a carboxylic acid salt is to call it a carboxylate. They both mean the exact same thing. Now, it says here that if we take a fatty, an ester or a triglyceride, if we take a triglyceride, so something that has a long fatty acid chain on it and we undergo the base catalyzed hydrolysis or saponification reaction, okay, in that case, we get the carboxylate, okay, but that is, in this case, it would be a soap. And if you're like, what? You didn't bring up soap before? Because before, when we talked about saponification, we were talking about making small carboxylates, like, you know, things like acetate, right? This is acetate. Acetate is not a soap because the chain, the hydrocarbon chain, is too small. It's just a methyl group, right? If we were to talk about ethanoate, so if we were to draw ethanoate, so that's got, or sorry, not ethanoate, propanoate, okay? So here's, I'll just use the common name, propionate. That also is not a soap, right? These are not soaps because they're too, the fatty acid tail is too short. But if we have a carboxylate or a carboxylic acid salt that has a long chain on it like this, forgive me for drawing like that, then you got a soap, okay? And then the soap, I explained earlier on in the course, forms micelles, right? I said that the non-polar tails will actually spontaneously conglomerate together, and then all the hydrophilic carboxylate heads will interact with water molecules on the exterior of that micelle, and of course, again, the hydrophobic tails will solubilize the dirt, oils, and grease, and that is how soap works. This is just showing a saponification reaction. I actually borrowed this picture at the bottom from a different textbook. So we have our ester plus a base produces a salt plus an alcohol. So recurring themes that you're going to see from the previous exam that can show up on exam 3 would be things like what? Esterification. You've seen that multiple times in this course. Saponification. Saponification. Acid hydrolysis of an ester. These are all concepts that we looked at in previous chapters and were covered on exam 2, but they can all show up in exam 3. Okay, so if you're like, oh, I think I mastered them now, well, now's the chance to redeem yourself or solidify your grade even further. And that should also impart to you that these reactions are extremely, extremely important in Chemistry 102. In fact, in the ACS final, I've given it to my students, you know, many, many times. So even though I don't have a copy of it, I've read the exam enough to know that I have a lot of it memorized. And there are many reactions. There's 100 questions on it. And there are several questions about esterification and saponification and hydrolysis of an ester. Okay, so those reactions are very important, if not some of the most important reactions in this class. With respect to hard water, so if I had an uncle in Canada, and at his house, you know, we'd go there and he always had hard water problems, which could be really irritating. It says that when hard water is used with soaps, hard water contains high concentrations of the alkaline earths, calcium and magnesium. So basically what happens is that the cations in the water, so the calcium or the magnesium, so we could write that down here. So the Ca2 plus or the magnesium 2 plus in the water can form fatty acid salts, like is shown down here. So instead of having a sodium cation or a lithium cation, you've got a calcium. So you need 2 fatty acids like that. And it basically forms these salts that precipitate out. So that's what causes soap scum. So if you've ever wondered, you know, what's soap scum? It's basically, you know, a carboxylate with a doubly charged ion. And also, it doesn't have to be necessarily calcium or magnesium. It can be iron as well. So there you go. So now you know where soap scum comes from if you've ever had well water before. So I should point that out that my uncle's house was on a well. So it wasn't on a city water system. And the city water, like that we have in Colorado Springs, for instance, that is, you know, purified and chlorinated or whatever before it reaches consumers. Anyhow, let's talk about phospholipids a little bit.